Ja, wie erwartet wurden wir unterbrochen, da ich keinen Speicher mehr. Oops. Like I was expecting, we were actually interrupted because I had no memory anymore. No memory left. I'm continuing here where we left with the displacement figure. So we had the displacement on the right here, delta H, we just give it the value 1, and we had found already that the body 2 is going to have a pure display, a pure translation. It means that if the left node is moving horizontally with the value 1 to the right node is going to move horizontally with the value delta H equal 1 to the right 2. And with that, we're basically done. Why do we need the displacement figure? We're going to use it to calculate the forces using the principle of virtual displacement. So what do? We say the following. The work actually of a force, the work of a force is basically force times displacement. Force times displacement. This is actually simplified. It's basically the scalar product of the force times the displacement, the scalar product of the force with the displacement vector of the application point of that force. So actually it's something like absolute value of the force times absolute value of that displacement times cosine of the angle between those two vectors. So if they're parallel to each other, the angle is going to be 0 and cosine 0 is 1. If they're like completely opposite to each other, the angle is going to be 180 degrees and the cosine of that is going to be -1. And if they got another angle between those, it's not just going to be the product of this. So this is too simplified. It's actually this. That's the work of a force. But yeah, let's just say force times displacement. If they're both going in the same direction, positive, both going in, if they're going in opposite direction, negative. Let's keep it simple first, but actually it's this. So what do we have? On our system, we have as external forces, we have the resultant Q times L. That force is a vertical force. But as you can see, the displacement occurring on this system are actually lateral. So what's going to happen for that force of ours? I'm going to draw the system here quickly. We got a displacement like this. This is basically what we had, and we have a force here, R, with the value Q times L, but the point of application of that force is moving like this. This is G, let's say, but you can see that the angle between R, between the force and G, is 90 degrees, and cosine 90 degrees is going to be, so it's going to be 0. So actually the work of that force R is R times G times cosine 90 degrees, and it's 0. So that force is not working. Or you can just say, okay, we have no displacement in the direction of that force, so there's no work and it's 0 for that force. What else do we have? The only other force we have is our force set 2, 0. That force is working. We have set 2, 0 is going to the left, and the displacement delta H is going to the right. So we got a negative work here with the value set 2, 0 times H, delta H, what 1 is, the value is 1. That's the work of our first set 2, 0. And the sum of the work should be 0. That's actually the principle of virtual displacement. So we have minus set 2, 0 times 1 plus 0 equals 0, so set 2 0, it's 0. Like I said, we didn't even need all of this. We could have said it from the very beginning. Pushing forward, we take the one state. In the one state, the unit state 1, unit state L1 equal to 1. What is L1? The restriction we made there. L1 was the rotational restriction, and actually finally I changed this position and I put it there, but let's just call it, even from here, let's call it R2. Okay, so now R1 is equal to 1. First, we just restricted those rotations and those displacement, and we left like the external load acting on the system. Now we remove the external load and we rotate, we move those restrictions. We put some restrictions, but in the reality they're not there. So we're going to apply them with a unit value, and our objective later is to find out how big is that value actually. So in the L1 case, we need to apply a rotation phi with the value 1 in the same direction as set 1 0. It's very important, in that same direction, or you're gonna have sign problems and stuff. It's gonna be really messy. So we rotate the whole thing with an angle phi, or R1 equal to 1, whatever. Okay, I really like to use the 45-degree angle. Generally you don't mess things up with that. And we draw the system as it's gonna deform. It's gonna look like that. This one's gonna go up and needs to come back down here. Yeah, I'm still using this line here to determine where's the positive side. Okay, and now let's draw those moments. Okay, they're only the right moment. You see, when I draw it like this is the right moment. That's how it is. I mean, on the positive face of the beam, and on the negative face, normally it will be in the other direction for the force method. But this is the displacement method. We just draw everything as it is on the right side. So that's why I draw them like that. Here I don't need to actually draw the moment because I know it's gonna be 0 here. Okay, the value we have in this case is 3 I over L to the power of 3. I'm gonna check the units here. This is gonna be for E, it's gonna be Newton per meter square times I. The whole thing here is Newton meter square divided by length to the power of 3. It's gonna be Newton per meter. It's gonna be Newton per meter. Okay, so it cannot be L square, it's just with Newton L. Yeah, okay, it's gonna be 3 EI over L. I was just checking the units because E, the Young's modulus, is gonna be Newton per meter square. For example, I is gonna be meter to the power of 4, and L here is gonna be meter. So on the numerator, I got Newton times meter square, and here meter, and I got this unit, that's the unit of a moment, Newton times meter. I was just checking if I need the L here, or just L to the power of 3 or something like that. That's the value. And here we got the 4 EI over L, and here 2 EI over L. We're working here with theory of first order, but if we were using the theory of second order, this here will be something, will have something to do with the A prime. This one will have something to do with the B prime. This one has something to do with the C prime. Okay, and they actually got certain values, but in theory, first order, the alpha is 0. That slenderness value is 0. So you just don't consider all those, the calculation that imply that alpha. So this is what we got. And just in case you want to know how this moment looks like, that 0 state, normally you don't need to draw it for the calculation, but I'm going to draw it here extra just for you to understand a little bit better what's happening and for you to understand better the compatibility, the equilibrium actually that we're going to do later. What we got there from the 0 state is the following result. Watch out. We basically got the following. Yeah. So this is what we got. This is our M0, let's call it like that. So we got a moment here, and unlike what we normally know, like when we got a moment on one side at the frame, that same moment just goes around the corner, except if we have a single moment that's applied there. Here, that moment is not going around the corner, it basically disappears. And the reason why it disappears actually why we got such a single moment acting there, and that's the moment that's the restricting moment, that's the value of the set 1 0 and that we calculated there. It takes that QL square if back to 0. Okay, but in reality this restriction is actually not there. So in reality we cannot expect this value of QL squared if just to disappear and come back to 0, because the restriction is not there in our actual system. Our actual system looks like this, and there's no restriction over there. So if I got a moment here, that same moment needs to go around the corner. Something like this needs to happen. If I got a moment here, it needs to go around the corner. It cannot just go back to 0. And I think you're seeing already what the equilibrium we have to do with. The equilibrium we have to make sure that the value we have here on the upper part, for example, of the moment should be the same as when we go around the corner. Make sure that there's no jump in the moment that's not supposed to be there. There's no jump that's not supposed to exist. And yeah, so we make further, and drawing this is not necessary, by the way, it's just for the calculation. Just needs to get the values, and we're gonna use some kind of superposition later. And what we got here from this system is basically the following. I'm gonna calculate the values that we need first. This is the K11, and this one is the K12. Okay, 2-1, sorry. The upper part, the upper digit here is the system, the unit state we're in. So the low state here is R1. We turn R1. That's the upper digit there. So, and when we rate it, we rate the lower digit first and then the upper digit. So this is K11, this is K21. Okay, so this is basically the force that we're gonna have at the position 2 caused by the rotation of, caused by the displacement R1, R1 equal 1. So when we rotate, because R1 is a rotation. And K12 later is gonna be like the rotation or the moment that we're gonna have at the position 1 caused by the displacement of the position 2, because position 2 is a force. And K11 and K12 and K21 should be the same. Like in the force method, when delta 1, 2 was supposed to be equal to delta 2, 1, that has to do with the theory of Betty Maxwell. Not theory, the law of Ritchie Maxwell. Yeah, let's say that I think it's law. So basically deformation caused by a force F applied, the deformation caused at the position J by force F applied at the position I is the same as the deformation caused by force F applied at position J. Is I just missed it a little bit. Position I and position J, and I have a force F here. The deformation that force F is gonna cause here at position J when it's applied at the position I is the same deformation that the same force F, if applied at the position J, is gonna cause at the position I. This deformation and this one are the same. Delta ij is equal to delta ji. Yeah. Moving forward here, we compute K11 through some of the moments around this node. What do we have there? K11. Blah, 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 blah. In this direction, 3 EI over L. In that one, 4 EI over L. So K11 is just 3 plus 4, 7 EI over L. That's a strange combination. The main diagonal should be positive, again like before in the force method. K11, K22, K33, when those digits are the same, the values should be positive. And K21 here, we're gonna get it again with the displacement, with the principle of virtual displacement. Okay, so how do we get it? I can draw the displacement figure here again. Looks like this. I thought about the work of a force already. Now I need to tell something about the work of a moment. So the work of a moment is basically like moment times the angle of the rotation of the body. And here we need to consider the direction in the sense of the rotation, basically like is the moment turning clockwise, is the moment turning in the same direction as the rotation of the body. If both of them are turning in the same direction, it's a positive work. If them are turning in different directions, it's a negative work. And the value of that work is just moment times angle of the rotation. So let's go to it. Principle of virtual displacement. Sum of the work should be equal to 0. The force, the K21 force is acting to the left times the displacement 1 acting to the right. That's a negative work. So minus K21 times 1. Plus, let's look at this beam here. We got these moments here, the 4 EI over L and the 2 EI over L. We can actually sum them up. They're like turning counterclockwise and the beam is rotating clockwise, so it's a negative work, minus a total of 6, 4 plus 2 there, 6 EI over L times phi, where phi is nothing else as 1 delta H over L is 1 over L, okay? Phi is just 1 over L. That's one work, and the other beam got a pure translation, so it's not rotating at all. So it doesn't matter that we got a moment here from 3 EI over L, it's not working because that beam is not rotating. The phi of this beam is 0. Phi 2 here is 0, no rotation. So we can just send the K12 over and we get, I should be equal to 0, we send the K12 over, so K21, sorry. So we got K21 equal to minus 6 E I S squared. Yo. Now we move to the unit state R2 equal to 1. Getting tired already. Unit state R2 equal to 1. So now what we move here, the displacement that we set free, again, not just setting free, but that we actually move, we actually realize the displacement with this one. We move this. It's important to move it exactly in the defined direction of the forces, in the defined direction of R2 from the very beginning. So we move it here to the left with a certain value R2 that we consider to be 1. So we shift the whole thing. We move it over here. And that's our force K2. When we move it to the left, what's happening? E is equal to infinity. So this beam here, this horizontal beam, cannot get shorter or something. The whole node needs to move too for that reason. And what's happening to the beam over here? It cannot get longer, but it can bend. I know this look like a beam that's longer is actually true, and at the same time not really. But this is only a deflection, a displacement in the direction perpendicular to the length direction of this vertical beam. So it's okay, we don't consider it as an elongation. And we still need to compute the same stuff. So the value here of K12, what should be equal to K21? We will still calculate it to check our values. But what we actually need here is K22. That needs to be calculated for sure. So, and what are those are what we have actually. The moment here is 0. I don't even know what I draw this. This is definitely 0 2. What do we want? We want this and we want that. Yeah, this value here are both the same and they are 6. Yeah, this is 6 EI over S squared, because we have a displacement from V, blah, blah. Yeah, exactly. 6 AI over S squared in the theory first order. Those are the values for theory first order. For theory second order, there's other alpha terms that are coming into play there. Yeah, and from those I can actually say already that K22 is actually 12 EI divided by S squared, then divided by L. I can actually say the following: K22 is 12 EI divided by, but let's check this. Okay, let's check that. And K12 is, well, we can see the value here already on that beam, on that node, and we do some of the moment should be 0. K12 here should be equal to this one. It's 6 EI over S squared. Is it what we had before? Not exactly. We had a negative value. Do I have a... this is a negative value too. Oh, nice. This is a negative value actually. I forgot the sign there. This is a negative. How do I say it? The tensile stress here is above. It means that this moment clockwise will have been positive, but here we have a counterclockwise moment, so it's negative. So I just forgot the sign. So it's actually a minus indeed. K12 is minus 6 EI over S squared. It's come from equilibrium here, minus 6 here over L square, okay, 1, 2. And K2 still need to be checked. We're going to do it with the principle of virtual displacement. Right now, I draw again. You don't need to do this like 1,000 times. You can just have it once, your displacement figure, only once somewhere, or maybe here, and use it like 1,000 times. You don't need to draw it again and again like I'm doing it here. Yo. That's our displacement figure. So what are we looking for K22? What do we have? K22 times 1 negative the displacement in this direction, the force in that direction. Then what else? The moments here are 0, and even if they weren't 0, this bar here is not rotating, so you have been a work of 0 anyway there, and we got those two moments from minus 6 and minus 6 again, so minus 12 EI over L squared multiply with the angle phi here is delta H over L, so 1 over L multiply with 1 over L. Now those moments are turning in this direction and the beam is rotating in the other direction, so it's a negative moment, so times minus again equals to 0. And then when I send this one over there, I get K22 times 1 equals to plus 12 EI over L to the power of 3. So I was fucking right. Validated. We got everything we needed. Let me draw for all those systems the moment distribution. How does it look? It's not necessary to do this during the solving of the exercise. I'm just doing it extra for understanding purposes. So we got here 3 EI over L, and then we go for that node and something like this happens. Suddenly we have 4 EI over L there, and then 2 EI over L over there. This is the moment distribution. You can see already an unusual jump here. Normally when you got like a frame like this and you got a moment on the outer part of the frame, let's say, when you go around the corner, that moment stays on the outer part. But here it's suddenly on the inside. It means we have a moment that's acting here. A moment that's acting in this direction. We have a moment acting in this direction. And that moment comes from the restriction that we have here. Okay. That was which value was that? It was the K11, yeah? It was the K11. Acting positive with 7 EI divided by L. That's actually the reason of the jump we had here. The K11 is the reason for this jump. And yeah, I don't need to draw the values actually of that K, of that force here. Don't need it. And for the last moment distribution, the one we just calculated, it looks like this. On this side there's like nothing. What's super odd is, and then suddenly we have minus 6 they say, so basically we got 6 EI over L square here, and then 6 EI over L square there. So what's our compatibility method? It's all about making sure that we don't have such jumps, because in reality we don't have this restriction. We cannot have a jump in the moment like from 6 ai over l squared to 0 without any acting moment there. Right now there's an acting moment coming from the restriction. The restriction in reality is not there. We don't have any restriction there. Let me remind you that our system actually looks like, oh wait, what's that system? Like I actually drew over it, but the system is actually just this. Just like this. There's no restriction here. And what else? Yeah, basically I can also say something about that support, but that was just like to give you the main idea what's actually happening here. That's what the compatibility is about. Compatibility that we're actually gonna just name equilibrium. So equilibrium, we say the following: Z10 plus A1 times K21 plus A2 times K, oops, A1 times K11, sorry, I was really confused there, and plus A2 times K12 equals to 0, and then Z2 0 plus A1 times K21 plus A2 times K22 is equal to 0. Yeah, that's what I basically explained about the moment. We want to make sure that we're going to have equilibrium about the moment around that place, that there's like no strange jump. And this here is basically about the forces acting at this position. We want to make sure that at the end this force is 0, because that force doesn't exist. That support, the support here is not existing at all in the real system. The real system got no horizontal force in that direction. So the sum of all those forces should finally disappear. That's what's happening here. And we need to solve this. We got two unknowns. I'm not gonna do this by hand, even though it's not that difficult. I'm just getting super tired here. So what are the values? Let's send this over there, R1, and we can write it like this, like a matrix: K11, K21, K22, K12, with the unknowns R1 and R2 should be equal to minus Z10, Z10, Z20, and we can actually input it like this in our calculators. Let's put some values in there. K11 is 7 AI over L. I'm gonna do it here. 7 EI over L times L1 plus K22, K12, sorry, or K21 is the same, minus 6 EI over L squared times R2 equals minus Z10. Z10 is Z10 is QL squared eighth, 1/8 of QL squared, also minus QL squared eighth, and then comes the say minus 6 AI over L squared times R2, and then the Z2 values, the K2 value is 12 AI plus 12 EI over L cubic times R2 equal minus Z0, that was 0. So minus 0 is just 0. And here we can simplify stuff for us a little bit and just take stuffs like actually we can just forget about the EI over L stuffs, just focus on the actual numbers, and then later just consider the actual unit we should have as solution. So what I'm gonna do here is I'm just gonna focus on those values. The 7 R1 minus 6 R2 equals minus 1/8, and the minus 6 R1 plus 12 R2 equals 0. I'm gonna do this equation times 2, then I will get like minus 12, and I could add them up so that R2 disappears. So times 2 here, times 2, times 2, and add them up. So this is 2 times equation 1 is that, and this equation 2, 2 times equation 1 plus equation 2, 14 minus 6, that's 8. R1 here we have 0, and there we have minus 1 fourth. So R1 is minus 1 32nd, and what is actually the value, we're gonna think about the unit later. And when I got that one, I can get R2 from the second equation. R2 is just half of R1, so it's like minus 1 over 64th, actually 64th of the unit that we're gonna get. So what are the units? When it comes to R1, think about it. Yeah, to get R1 alone here, I basically need to multiply the QL squared divided by 8 with L, and divide with, I multiply with L and divide it with EI. So it's R1 got the unit Q L to the power of 3 divided by EI. And that's actually matched for a rotation. And a displacement is supposed to be something like Q to L to the power of 4 divided by EI. Let's see if it's matched for R2. I need to multiply this unit with L squared divided by EI. It matches. QL to the power of 4 divided by EI. Those are our values. We could also input this in a calculator, and yeah, if your calculator can do that, you're lucky. And yeah, those are the values we were looking for. And now we can do a superposition. How do we do that? Like before, like in the force method, like with the force method, the superposition is M total is equal to M0 plus R1 times M1 plus R2 times M2. And we got the different M already. I drew them explicitly, even though they're not necessary. What someone can also do is just to record those values and give them names. Say, okay, this is M1, 2, whatever. So someone got a system like this. This is node 1, node 2, node 3. The moment over here is 1, 2. The moment over here on this side is 2, 1. The moment at this frame, but on the horizontal beam is 2, 3. And the moment on this beam is 3, 2. Okay, as I hope you see the logic there. From 3 in the direction of 2, from 2 in the direction of 3, from 2 in the direction of 1, and from 1 in the direction of 2. That's how we can actually identify all those values. And in the exponent, let's say you say M1, 2, you can add in the exponent 0 if it's the 0 case, 1 if it's the 1 case, 2 if it's the 2 case. Can add those information, and then just write the matrix here and do all the sum. Say M1, 2, M2, 3, and blah, 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 and do all the sum. I don't want to do it that way. Okay, let's do it that way. I'm so tired. I basically haven't slept. M1, 2, yeah, M1, 2, M2, 1, M2, 3, and M3, 2 should be 0 anyway, so I don't even really need to compute that one. And M2, 1, so the moment over here, M2, 1 and M2, 3 should be the same. So normally I don't even need to compute both of those, I just need one of those. But as a verification, we can compute like the two of them. This one doesn't really need to be computed because it should be 0. That's a verification, we can also compute it. So the M0 values, M1, 2 in the 0 case, what is it? It's 0. M2, 1 in the 0 case, it's 0. M2, 3 in the 0 case is QL squared to the power of 8. QL squared 1/8 of QL squared. M3, 2 is 0. It should actually be 0 in all cases. That's why it wasn't necessary to compute it. Plus L1. Let me remind you of the value. Hoping that I got that part right. The value is minus 1. It's 1/64th of QL to the power of 4 divided by EI. That's a rotation times, we got now the values in here for M1. Actually, I'm just reading them here because I do it already. Actually makes us a little bit easy. When you think about it, M1, 2 here is 2 EI, so 2 EI over L. Gesundheit. EI over L. M2, 1 is 4 EI over L. M2, 3 is that 3 here, 3 EI over L, and M3, 2 it's 0, like it's always gonna be. And finally R2 with the value Oh, the minus 164 was actually the value of R2. The value of R1 is minus 1/32 QL to the power of 3 divided by EI. Yeah. So, and the value of the moment here for M2, first minus 6 AI divided by L square, then minus 6 AI divided by L squared again, then 0 and 0. Okay, so the resulting moment is first it got the value, the EI are gonna cancel out, as you can see already. At the end of this, we're gonna have a QL square. Even here it's gonna be a QL square coming out of it, so as expected for the unit of a moment. So we just need to calculate those values. The 0 in the first case is basically 0 minus 1 over 32 times 2 plus minus 1 over 64 times minus 6, so plus 6 over 64. This is 465 multiplied by 2 is minus 4 over 64 plus 6 over 64 is 2 over 64, so 1 over 32. So 1 over 32 QL square. That was the first one, the first value. The second value is minus 1 over 32 times 4 minus 1 over 64 times minus 6. So it's 8 over 64 plus 6 over 64 minus 8 over 64 plus 8 over 64, that's 2 over 64 equals 1 over 32. Like I said, those no, that's not what I thought. I thought it was M21 and M23, they should have the same value at the end, but no, that's like not what I thought. But they should also have the same value, those here, if someone got an idea how the distribution should look like at the end. I think I drew it somewhere. It should basically looks like something like this. So it's constant here. Why is it constant here? It's because we don't have any force in the horizontal direction here. So the shear force in this vertical beam is 0. If the shear force is 0, it means the slope of the moment is 0, meaning the moment is constant. That's why the value should be the same here. Let's keep going. Let's keep pushing. The third value is 1/8 of QL squared. Let's put it here. I'm sorry, for a while I haven't really been checking if you actually see what I write on the camera. I'm really sorry, like my head is all over the place now. 1/8, are you making fun of me? No. Okay. 1/8 of QL squared. I'm not going to write the QL square thing. Minus 1 over 32 of 1 over 32 times 3. Minus 1 over 64 times 0. Oh, thank God, that's 0. Here to get the 32, I can multiply by 4, so it's 4 over 32 minus 3 over 32, that's 1 over 32. Yeah, we got the same value M21 should be equal to M23. M21 should be equal to M23, like I said, because we go around that corner. That's one of the main compatibility stuff we want to have respected. And the value here should be 0. We have 0 there, 0, 0, 0. It's just 0. We got it. So our moment actually, we're not completely done. We need to check something else. Some of the values here, we were still using the following convention, the convention of the displacement method. So everything on the right, on the positive face, the positive cut is actually called positive face. On the positive face of the beam, it's okay, but everything on the negative face need to be inverted. So when it comes to, let's draw our system again. Where are we? This is our system. The values like M32, this no 2, no M32 is okay. We don't need to change anything with the sign. That 0 is definitely a 0. Even if we had to change the sign, it wouldn't matter. It's 0. The value on, when we look at like this, on the right side, the value here for M21, it's also okay. So the second value is also okay. It's 1 over 32 for QL squared. So 1 over 32 positive on QL squared, like this. What? Like, wait. Wait, there's something wrong here. The 2-1 value, yeah, should not be changed. And that's 1 over 32. Okay, something definitely went wrong here. I'm gonna check. We have a mistake there. Should not be changed, and if it's there, we got a positive value, so it's positive. Is it actually positive? Need to check it again. First we got 0, and then minus 1 over 10.